And we're live. I was actually, our producer's having internet connection problems. I was afraid, what if she loses connection while we're waiting for the go command? So
That's
welcome.
right.
Hey,
Yeah,
Bert.
welcome to our second day of review. Hi, Mark. How you doing?
Doing all right.
Good.
So I am Mark Corelli from Ryan High School in Denton, Texas.
And
And
I'm Verge Cornelius. I'm from Lafayette High School in Oxford, Mississippi.
this overview is for where we're headed before May 1st, right? Before we actually, well, maybe May 8th, we'll see. But this is our plan for review, getting through these units. It's really small on screen. That's okay. You can take a screenshot or you can take a picture of this QR code, click that link. It's at the top level of our Dropbox. So if you go to the Dropbox link, which will be shown at the end of the video, it's in the description below. You can go, it's at the top level. It just says schedule from April 13th to May 1st. So.
Or you can not worry about it and just join us every
show
day.
Up, yes.
Because you know what? You guys are awesome. We had, I think, the second most number of views yesterday. And that's amazing because we were only behind a class, a course that has way more students than AB Calculus. But everybody came to ours and yay for you.
All right. So this slide again, if you go to apcoronavirusupdates.collegeboard.org, you can get all this information. I think we've covered it, but expecting 2 free response questions of 25 minutes and 15 minutes coming up on May 12th. So
that's right. And we've had some questions from teachers about the AP exam. And so definitely go and do some of that research on that site so that you know it's ready, you know what's happening for your students.
And I think this is, hey, 3 days without mistakes. So.
Yay! We're gonna go for 4 today. Today's an easy day.
Yeah, oh, way to jinx it.
So yeah, we didn't have any mistakes in the last 3 classes.
All right, so we've checked off our first bullet here. It is April 14th. I think the next slide, I may not have changed that. We'll have to check. We're going to do our warm up. We're going to talk about derivative definition and basic rules of differentiation. And then we'll wrap up and let you know what is already in that Dropbox if you haven't gotten it already. Oh, I got the date right. Good.
Yay.
So here's a couple warm-ups. If you want to say anything about them, you want me to read them, Verge? Or?
Well, no, we worked on limits yesterday, so we thought it would be good to give you a couple limits as practice. We did discuss whether or not we wanted to do some of those problems from our notes pages yesterday as our warm-up, but we're probably moving those to Friday. So these are limits that we intentionally pick, not just to keep you busy, but to try and bridge us over to what our lesson is about today. So you can evaluate those, just straight up evaluate them using some direct substitution or algebraic techniques or whatever. But you might also think about, why did they pick those? All right. Do you want me to tell a joke or nah?
Well, I expect you to.
Okay, here's the joke. Why couldn't the angle get a loan?
Okay, so probably going to avoid the acute. So why did the angle get a, why could not? Is that why is it couldn't?
Well, yeah, why couldn't the angle get a loan?
Why couldn't the angle get a loan, Verge?
Because its parents wouldn't cosine.
Nice.
All right, Mark, are you going to steal the screen to go over the warm-ups?
Sure. Yes, let's.
Okay. So this is the limit as x approaches 4. As he's doing that, the limit as x approaches 4 of x squared minus 16 over x minus 4. You probably try a direct substitution first. That doesn't work for you because it's an indeterminate form. So you try and do something else, such as what?
So we have x squared minus 16 over x minus 4. Is that correct? Mm-hmm. Yes. And if we plug in, we get that indeterminate 0 over 0. And so we know that didn't work. But the 0 over 0 is a clue that there might be something more going on. So when I teach Algebra 1, my Algebra 2 kids, I always say this: if they see 2 squares with a minus, that should set off a bell in their head. Ding, 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 ding.
Like that?
Yeah, difference of 2
or
squares.
Or more like this. Whoop, whoop,
yeah,
whoop,
something
whoop.
Pavlovian. It should ring a bell. Because that's definitely something where and when I haven't taught algebra in a while, but the last time I taught algebra 1, we did 50 of those a day until everyone got them right. And it took 2 days. They didn't believe me the first day. And then I can cancel those because it's in a limit, right? So that'll be the same as the limit as x approaches 4 of x plus 4. And now direct substitution works, and I get a limit of 8.
Yes.
All right. And my second one, if you want to read that to me.
Sure. It's the limit as h approaches 0 of, in the numerator, x plus h quantity squared minus x squared. Okay, you remembered it.
Yeah, so you said h. I was like, oh, right.
Oh, yeah, because we kind of know where this is going.
I also have inside information as the author of the problem. You know? I'm sure I'm not the first one to have written it, though. All right.
Oh, yeah,
okay, so you want to use conjugates here, Virg?
No, sir. That would be for a square root.
Yeah, and if I plug in the 0, if we try the substitution method again, you'll see that I get x squared minus x squared on top and 0 in the denominator. You'll also notice my notation of limit gets sloppier and sloppier as the problem continues. So x plus h squared, that's an x squared, and then we do that distribution of x times h and h times x. So 2 xh's and then an h times h, and I misspelled my addition sign.
Just turn it 90 degrees. There you go.
That's right. Over h. And now some stuff goes, right? Because I've got those guys can take each other out. I'll have a good time wherever they go. Sorry, I can't help it. It's reflexive.
I've never heard that one before.
Oh yeah,
Where do they go?
Yeah, I've got a bunch like that. Like, how do we get x alone? Well, we bought a couple drinks, and all right, we'll factor an h out. Why am I factoring an h out?
You're gonna go ahead and h divided by h, as long as h is not 0, is 1, and so that will cancel.
Yeah. And then using that direct substitution, I get 2x plus 0, or simply 2x. And so my answer is in terms of x, because we didn't know what x was. We know h is approaching 0, but we have no idea what our x is doing. So, which is how it should be. All right. So you want to say anything about these guys?
So to me, and I was thinking about this before we went live today. It's kind of like we're doing the prequels now, Mark. Like we had episodes 7 and 8, and now we're coming back to see where it all came from. And when you watch a prequel, especially if you've enjoyed the movie in the first place, which is why you're watching the prequel, you're like, oh my gosh, that totally makes sense. Anakin is Darth Vader. I get it now. So like here, when I look at this, I'm like, oh my gosh, limit definition of the derivative. I get it now. So that's where we're going with this.
That's actually funny, because if you go from another point of view, speaking of, is if it's actually written in the correct order and you're not making it up as you go along, then you see the problems where you look back at your chapter 1 stuff. If you guys go back and look in your book now and you're like, oh my gosh, look how many derivatives I was doing when I didn't know what a derivative was.
Exactly. And why did the teacher know it so quickly walking around the classroom?
Why did we have all these h's in our thing and all these x plus and minus in the denominators?
Yeah.
Well, where did we come from, right?
Right.
And so that's today's stuff. Is this where we're going next?
Yes, sir. Limit definition of the derivative in the alternate form.
And this page that you can see here is in the Dropbox already, or should be. If it's not, I apologize. And I'm sure my friends from Minnesota and Arizona will let me know, as well as a couple watching in Texas that I know of.
But the intention here is for you to do some guided notes and have a nice review sheet for yourself when you're done.
So when we're finding a derivative, we're finding the limit of the slope. So that's always in my mind. I'm going to actually put a third column here in the middle of just kind of a thought bubble. And this slope formula we used to play with all the time. And I usually did delta y over delta x, but that can also be written as, f of x2 minus f of x1 over x2 minus x1. And that's really what we're playing with. We're trying to find this as those points get closer and closer and closer together. They're kind of approaching each other. And when do we play with approaching? Well, back here with a limit, right? Here we're getting closer and closer together. And I'm actually going to look at the blue one here because that is our limit definition. What was the function here? Well, if I look
f of
back,
x was x squared.
yeah, so there's f of x. And if f of x is x squared, f prime of x is that guy. So how do we get there? Well, we take the limit, and what we're going to do is we know f of x, and we're just going to move a smidge over. A very technical term in mathematics, correct?
Mm-hmm.
Yes, a smidge. So we're moving over h, and this is my 2 points now. That's my 2 y values. And we want h to get smaller and smaller and smaller. And what would my denominator be if I wrote this the way I wrote it over here?
X plus h minus x, or just
that-
h actually.
And that
yeah.
x minus x can take each other out
Mm-hmm.
and leave behind just h in the denominator.
Mm-hmm.
So that's where the limit definition of our derivative comes from. Some of the books use delta x for h. It doesn't matter. If you wanted to find the derivative at a point, you can do 2 plus h and f of 2 here, and then you can find the derivative at 2 exactly, directly.
Mm-hmm.
Right? And then there's an alternate form. And the alternate form, not a coincidence, looks a lot like this.
Mm-hmm.
Because here my function was x squared, my x value was 4, and there's my 4 squared. So
And what's the derivative of x squared? 2x.
Yeah.
And what's
so it
2
should have been
times
2
4?
times 4.
Yep.
Yes, we found the derivative of x squared twice already today. So the limit as x approaches some value a, and then I just take my function, subtracting, evaluating at that point, and that's my x2 and my x1. So x minus a in the denominator, and that's considered the alternate form. And this one is f prime at a, and this one is f prime at x.
Mm-hmm.
Yay, I think I did that right.
Yeah, it's excellent.
I'm really glad I have 4 sets of eyes on this because
Mm-hmm.
that's all right. So notations.
Actually, I have glasses on, so that's.
I almost said 6, but I didn't want to be that guy. And now
that's okay. There
That's
were a
it
lot
now.
of those guys in 2nd grade, and look at where I am now.
All right. Just remember that. Just complex conjugate theorem. The eyes always come in pairs. That's all right. So f prime of x is obviously one way to write a derivative. We can also write it as the derivative with respect to x of f of x. If y equals f of x, then it can be dy dx,
Mm-hmm.
y prime. Are there any other notations I'm not including? Well, this one you don't see on AP very often, but that is actually a notation for derivative. Actually, when I say very often, you will never see it on your AP exam. You can find it on older exams.
Mm-hmm. And because this is a prequel, I don't think I'm getting too. I don't think it's too bad to say things like this is the first derivative.
Yep.
Of course, we can always talk about like the second derivative and higher order derivatives, which is going to really, we'll talk about those tomorrow, but we know those notations as well.
And then this one, right?
Yeah.
So the nth derivative, that does show up on the AP test. In fact, a few years ago, there was a 4 that really set a lot of people. And the BC kids, if you're a BC kid watching this, and welcome, I'm glad you are.
I bet you that's why our numbers are high, actually,
Yeah,
because there are some BC kids.
The BC students are much more familiar with that because it has applications in that unit 10. So, all right. I think I'm trying to think if there's any other. I guess. Oh, we should also do 2 derivatives of y with respect to x both times, right?
Yep.
Or because that's the man, what great notation. So, yeah, and we're I believe this is the Leibniz notation, and I believe this is was it Lagrange?
I think we looked that up, Lagrange, yeah. And then Newton's notation is, we're not even going to.
Yeah,
you can look that up on your own. It went by the wayside.
If your physics teachers ever do something with dots, that's what it was.
That's from Newton.
Oh, hey, we have 6 biological eyes was just pointed out to me in the chat box.
Oh, because our
So,
producer
yeah,
has her glasses
yeah.
on. Yeah.
No, and she's here as well. Just
Oh.
I didn't count her when I did my 4.
Uh-huh.
All right. Do you want me to do this one or?
No, keep going and do the
Okay.
differentiability, and then I'll take it over from the derivatives.
Okay. So what derivative tells us that x equals a? Well, what does it tell us? We're taking a slope. We're going incrementally smaller. So we're going from the slope of a secant line, and then we move that over and we start getting these guys, right? Here's a better secant line. And eventually I find the slope of the locally tangent line. And I'm going to just put that in quotes. I'm also going to separate that. And I say locally because we know if this is a polynomial or a sine wave or a cosine wave, it very might turn back and hit the tangent line again, and it kind of breaks that tangent line to a circle definition we all learned in geometry. But in this area, hits it at one point, that's the slope. Also can be, and this is the one I always like, instantaneous rate of change, right?
Yes.
Slope of the tangent, slope of the function. And I guess I should say instantaneous rate of change of the function, right? Because it itself, of whatever function you're looking at, the second derivative is the instantaneous rate of change of the first derivative and so on. Slope of the function, oh, what else can it be?
Well, it could be instantaneous velocity for, I mean,
Yeah.
well, yeah,
Context,
it depends on the
right?
function. Yeah,
In
contextual
context,
stuff.
it's the instantaneous rate of whatever your function is. Yeah. So,
Yep. Good.
And then, because I do want to say first derivative is velocity if it's in motion, but it's not
True.
velocity if we're talking about water going into a tank, unless you're actually measuring the actual velocity of the particles of water. So. Which is an interesting question. It's always in flux. Anything else?
I think that's good.
I think we covered it. So I think at this point I'm handing off to you on the differentiability.
No, keep going.
Oh, I have to do this one.
Yeah, you're good at this. I think just talking about how do we know that something is differentiable?
So differentiable as well, first of all, differentiable, remember, to find a derivative. Derivatate? No, that's what we don't say. To find a derivative is called differentiating, right? We differentiate. And so differentiation means we can differentiate. So the derivative exists. And I'm having trouble with my spelling of derivative all of a sudden.
Well, that's okay. So does Microsoft Word. It always squiggly underlines.
So the derivative exists.
And yeah,
that's what differentiability is. The derivative exists at every point where the function is differentiable. We don't say we derive the derivative because derive means to find a function and was already taken. I did have a class one year that called it derivatizing. So I probably shouldn't have said that out loud to thousands of people. But differentiate is the derivative exists. For the derivative exists, that means the function is smooth. And there actually is a formal definition of smooth, but I'm putting in quotes because I'm not going to get into the formal definition. But I guess what's easier to say is, where is it not differentiable? Where can the derivative not exist, Verge?
At a corner, like
corner.
Like an absolute value function will have a place of non-differentiability, or at a cusp.
Yep, the seagulls that I still draw this way.
That's a cusp, or perhaps at a vertical tangent, like cube root of x.
Yeah, that instantaneous vertical. Yeah, nice.
And of course, if a function is not continuous at a point, then it's definitely not going to be differentiable there.
Right. So it has to be continuous. And that is huge. If you guys, this is your review notes anyway, so it's all special stuff, but
later on when we talk about like oh, this function is differentiable. Well, differentiability implies continuity. So that is a leap that a lot of times you have to make on a justification.
A couple of the problems we gave you yesterday, we cheated. We said the functions are continuous, and in reality, the original problem said G's differentiable, and then you have to make that connection, and you have to write that connection, because we, as readers, Virgil and I have both read, and as readers, we only know what you write. We don't know what you know. I can't feel the paper and be like, no, they didn't know.
You have to be explicit.
And NTK down here is need to know for those of you that aren't familiar. So has to be continuous to be differentiable. So this does imply that. Continuity, maybe it's differentiable if I know continuity, right? Because these are continuous curves where they have points that aren't differentiable. So differentiability implies continuity, but not necessarily vice versa. In continuity, we those 3 bullets yesterday, right? F of A exists. The limit as x approaches A exists. And those 2 are equal.
So if you're asked to check for differentiability, you need to first check for continuity. In my opinion, that's what I always teach my students.
It's a lot easier to rule these out before you have to investigate these situations. Absolutely. And
because those situations have to do with abrupt changes in slope, so you need to consider the slope from both sides.
Yep. Neat.
All right. Should I steal the screen?
You may steal the screen.
Okay. So those of you who've been with us for several weeks, boy, do we love you. And also those of you who are just us, I need to remind myself every day what day it is. It's Taco Tuesday, and this is Unit 2 of derivatives. It's our 15th AP Live, so if you don't have any more Tiger Kings to watch, you can go back and watch some old AP Lives.
15.
It's crazy, but I talked a lot about the yellow sheet in our previous videos, and so I want to talk a little bit about what that yellow sheet might look like. It's not something I do for the students. They make it 100% for themselves, but these are the kind of things that would be on it. So for derivatives, they would need to have on their yellow sheet somewhere the derivative with respect to x of sine x. And so I'm just going to say equals cosine x. Maybe you were sitting and listening to everything we were just saying, and you've already filled out this entire thing yourself. Derivative with respect to x of e to the x. Again, this is the prequel. We already have been working with these antiderivatives, so I'm not going to spend time proving why that is, or having you guys draw out the slopes or whatever like I would in my own classroom. But the derivative of e to the x is e to the x. Power rule, that's a biggie. Derivative with respect to x of a x to the n. Take that n, multiply it by a, and you get n times a, x to the n minus 1. You can see that one, it's kind of blending in. How about this derivative down here? Go ahead, Mark.
I'm just going to interrupt because I just took a moment to look at my text messages, and somebody said yes, definitely Lagrange, and sent me a link. I just, a little secret. If I say I think, I usually I know.
Yes, I know. This one down here, derivative with respect to x of cosine x, that is negative sine SINE of x.
Yes. It's important that G makes a difference.
Here, derivative with respect to x of natural log of x is 1 over x. Again, if you watched all of our videos those last 2 weeks or so, you know that we've gone backwards on all these. Derivative with respect to x of 1 over x, you can write that doing a power rule. We developed this idea so deeply in my classroom that most of my students actually have that memorized. You get negative 1 over x squared. Same idea here, derivative with respect to x of the square root of x. We developed that idea pretty deeply in my classroom, justifying it with limit definition and stuff like that. You can do it with power rule. You get 1 over 2 root x. Then finally up here, these are the biggies. Product rule and quotient rule. So the derivative of a product, and your teacher might have used U's and V's ddx of u times v, for example. But I'm going to go ahead and use f and g. This derivative of the product, in other words, these are being multiplied together, is going to be the first f of x times the derivative of the second, so times g prime, and then plus g of x, the second, times the derivative of the first, f prime. And that is the product rule. Addition and multiplication are commutative, so it doesn't really matter which one you decide is your first, you know?
Yeah, at this point in the year, most of you are probably comfortable enough that you just kind of put it where you want to put it.
This one here, the quotient rule, derivative with respect to x of f of x over g of x. This one is low-de high, mine high-de low, oh, low, low. So low meaning the denominator. Oh my goodness. The denominator, the abominator.
Denominator. It's not to be, because the other one's the numeroperator.
Okay, the numeroperator. So we've got low-de high, so that the denominator times the derivative of the numerator. Low-de high. It's like singing the alphabet. You got to start back at the beginning again. Low-de high, mine high, that's f of x, d low times g prime of x, o low low, over the denominator squared. And I'm just going to use brackets there for clarity. You can, of course, use parentheses there.
I'm going to also take a chance to just apologize to all the kids in Denton, Texas, specifically in the Ryan zone, because I don't sing. So.
Oh, well, I could sing. Actually, there's 3 songs for this for this week. Yesterday, I should have sung "Take It to the Limit" one more time, and then I could have said derivatives, they help us find the rate of change. Okay, you have opened a can of worms there, Mark. All right,
awesome.
Anyway, this is awesome. This is just a smattering of what could be on somebody's yellow sheet as they're preparing a study guide for themselves, not the teacher preparing it for them. All right, so in our shared folder, we have a circuit, a full-on circuit here, product and quotient rules. And actually, because this is a prequel, you actually know about chain rule. So if you prefer to do some of these questions using chain rule, because you know chain rule, of course you can. But I thought I might do a few of them to you right now that are just kind of interesting. So for example, this one right here is interesting. This one is y equals tangent of x. I mean, at this point, hopefully you have that memorized, or at least you know that you had it memorized at one point. It'll be easy to rememorize for yourself. But remember, these are all derived from either quotient or product rule. So if I want to take the derivative of tangent x and I forget how to do it, I could just derive it again for myself. So derivative of tangent x would be the derivative of sine x over cosine x. So y prime or dy dx would be low-de high, so that's cosine x times derivative of sine cosine x, mine high-de low, so minus the numerator times the derivative of the denominator. Derivative of cosine is negative sine x, o low low, over the denominator squared. And then this is really ends up being a trig identity in the numerator. Cosine x times cosine x is cosine squared x. Negative sine x times negative sine x is positive sine squared x.
Ooh.
I know. When you were talking about the alarm bells going off.
Yeah, one just went off.
Boop, 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 boop. What's the numerator, Mark?
E to the 0.
Okay. 1.
Sorry.
No problem. So this is 1 over cosine squared x, which is the same as secant squared x. So perhaps on this right here, I might write it down for myself. The derivative with respect to x of the tangent of x is equal to secant squared x. Realistically, on the AP exam, and Mark, you can disagree if you want, but there's not a lot of like trig identities or heavy trig really on AB anyway. However, in real life, there's a lot of it. So I need to, as a teacher, I've always kind of gone in the middle. Like I want to, as soon as they've forgotten a trig identity, I want to bring it back again. So anyway, I'll prove this stuff a lot for my students just to keep it fresh for them. Okay, another one that I thought was interesting to do on here was, and then Mark's going to do a few problems, was this one here. Because to me, this is a very AP question. Given f of 5 is equal to 3, f prime of 5 is equal to 3x plus 7, g of 5 is equal to 2x minus 1, g of 5 is equal to half, then this is the statement. If k of t is equal to this quotient, g of t over f of t, calculate k prime of 5. So here we go again, quotient rule, third time's a charm. I gotta figure out the derivative here, and then I've got to calculate, substitute in a 5 and actually get some sort of a result. So let's see what happens. So k prime of t is going to be loady high. So careful. This is why I don't have things memorized with F's and G's. I have things memorized with first and second and low and high. That's, that's just a tip.
A very important tip.
Yeah. Oh, thank you, Mark.
They've done G of F on the exam before, and poor kids.
Oh, you're talking about tomorrow, chain rule. Yeah.
Oh no, they did a quotient rule with G over F.
Oh, I thought you said G of F just now.
Yeah, sorry, no, G over F. Yeah.
Okay, yeah. Low, D high, mine high. D low, D D, oh low, low. So, yeah. Okay. All right, so that's my symbolic derivative there, and now I need to start kind of plugging stuff in. I'm going to actually scoot it up and just use my white paper right here so I don't have to run out of room. Let me, oh, that's fine. All right, so anyway, f of t, let's see. F of t is
at 5, right?
Yeah, oh yeah, well, I guess that's true. We were looking at 5. So f of t at 5 is f of 5 is 3. And then times g prime of 5. G prime of 5 is a half.
Yep.
And then minus g of 5, because we're evaluating at 5, is 2x minus 1.
Sounds like 9.
Oh, because x is 5.
I want that x and that t. It makes you want to plug the 5 in, but you're right.
Oh, yeah, no, we can't do that. Okay,
Yeah.
and then f prime at 5 is going to be 3x plus 7. X and t are not the same variable.
No.
And then this is all equaling k prime of 5. And then over f of t quantity squared. So f of 5 is 3. There's a 9 there for you, Mark.
Yay.
Yay, 3 squared in the denominator. Okay, so this is 3 times a half is 1.5 minus, and then just, PSA, when you have quotient rule, there are lots of issues distributing. Students will distribute to the first term, but not any of the rest of them, and that's bad news. Anyway, so go ahead and get this all expanded in the blah, blah, blah. I think this is a plus 11x.
Yep.
And then minus a 7. And so this ends up equaling, well, if it were the AP exam, you really could leave it right here, to be honest with you. But in real life, you'd have to finish it out. So I'm just going to go ahead and finish it a little bit of the way out. That's good enough. Anyway, but those are just a few examples of using some of the rules of derivatives, in particular quotient rule. But Mark's going to go ahead and do a 4 corners with us, which is that in the Dropbox right now or not?
It is. And this was originally written by Brian Passwater. We did change a couple of the problems because they had some chain rule and we didn't want to do chain rule today. And I also prettied it up because I wanted it to look like our branding or whatever you want to call whatever version I've produced over the last 15 lessons. Okay, so if you're not familiar with the 4 corners, the way this looks is it's derivative rule 11 or rule 1, level 1, sorry. And then there's analytical, numerical, graphical, and verbal or conceptual, these 4 ways of representing rules. And so we're going to go through one of each and got about 10 minutes left. That should be plenty of time.
Mhm.
All right, and I'm glad Verge went first on these because I do product rule, I call it left hand because I do F prime G instead of G prime F to start. And it doesn't matter, right? Because the multiplication is commutative, the addition is commutative. And honestly, what I tend to do is what looks easiest to me. And so Verge
Hey,
is
I've heard
commenting on
that
that. I was
before.
gonna say, Verge has commented before about looking what's easiest, right? So the derivative of x squared to me is easier than the trig function. So sorry, I'm going to move my camera here. I realize I'm leaning out of camera when I'm. All right, so we get 2x, and then times cosine of x. Only take one derivative at a time. That's real important throughout the whole course. It's just don't take two derivatives at the same time. You're probably doing something wrong. And then plus x squared, and then the derivative of the cosine x is negative sine x. And like Verge said, this was an open-ended. You could leave it like that. I'd probably clean it up. So 2x cosine x minus x squared sine x. And that's about all you can do with it. You can factor an x out, but that's just your pure analytical. That's f prime of x. And if you had negative x squared sine x plus 2x cosine x, you have the same answer. That's fine. All right. A numerical. This is actually the problem Verge just did was like this. Except instead of a table, these values were given as a list. But
and some of my given information was actually like an expression.
Was still analytical, yeah.
Yeah. So it was,
all right. So Verge, you want to tell me why I can't just go ahead and plug in k of -1 and 3 times -1 and then take the derivative?
Well, a couple of things. First of all, you always take the derivative before you plug in. Second of all, if you did that, then you would be getting 0 every time, and you should be by about October wondering why you kept getting zeros every time.
I always get, my answer is always 0. So we actually have to find h prime of x before we can find h prime of -1 because it's instantaneous rate of change. And if you plug in constants don't change. I always told my wife I want to name our daughter Constance just so I could say, Constance, you never change. Okay, so derivative of the top times the denominator minus derivative of the denominator times the numerator all over that low or denominator squared. And there is going to be a printed key for this in a couple days in the Dropbox. We're giving you guys a couple days to work on before we clean things up and put it in the key because we want to make you have the intellectual struggle. And that's a good phrase. That's not a bad thing. Only thing I'm really going to clean up is I'm going to throw those constant coefficients in front and that 9x squared I'm going to clean up. I did on that key you'll see in a couple days. I did go ahead and do more. But I think at this one, plugging in the -1 actually isn't too bad. In fact, -1 is really easy to work with.
I probably would have plugged in like 3 times -1 and then squared the -3 personally.
Yeah, exactly. Yeah, there's all kinds of fun stuff we could do. So k prime at -1. There's my -1. There's my k prime. So that's going to be 4. So -3 times 4 down there at the bottom. And then -3 and k of -1 is -3. I meant the sounds again. And then that looks like -12 plus 9 over 9.
Slide it up just a little bit.
Oh, thank you. And -3 over 9 is going to be -1/3. So cancel the 9s. No, don't do that. So, yay. And I believe that's the answer I got earlier. So that makes
it is. And it's the answer I got too. How good is that?
So let that up there for you if you want to take a second. And then moving on to the graphical. I love this one. I like this style of problem. Wait a minute. We hadn't talked about graphs today.
Every day, talk about
your graph is much prettier. Part of this being stay-at-home stuff is I print black and white beautifully. I can't print any graphics right now off my printer because I'm just parts missing. Toner specifically. Let's see. So we're looking at p prime of 3, but again, that means I need to find p prime analytically first. So we're going to go, let's see, we'll do it with the way Verge does it, where we go 5x times g prime plus 5, the derivative of 5x is 5 times g of x. And then we're going to plug in 3. G prime at 3. Okay, well, I have the graph of G here, and this is a line segment. It's very clear on the actual graph. It's a line segment. If this were an AP problem, they would have said the piecewise function G made up of 3 line segments.
Or they would have said piecewise linear function G.
Right. So this is a line, and it goes down 2 over 1, down 2 over 1. So that entire thing has a slope, which is G prime for that interval, of -2. Plus 5 times g of x, or g of 3, is just 0. Just pulling that off the point. So I just think that's cool. You're still pulling stuff off above, just like we did with the table up in the upper right, but now we're getting to pull values off of the graph. And 15 times 2 is going to be 30, negative variety because of that 2, plus a 0. So p prime of 3 is -30. All right. And the conceptual verbal here, it's more conceptual than verbal, because we don't really have a context when we're learning our basic rules. But I've been given a function g of x is e to x, and f of x is 3 times g of x minus x squared plus 3. Find the derivative at 2. We didn't talk about the properties because this is a review class, or review session. But when I take the derivative of a difference or a sum, I can just take the derivative of each part. And then what I look for is, do I need product rule? On that term, how many x's do you see, Verge?
1. I'm glad you're
1x.
saying this because this is exactly what would have talked about as well.
If there was an x on the outside, I would need to do a product rule, but that 3 is a constant. It is just stretching that graph, stretching its slope. It's not a separate function of x. So it's along for the ride. 3 times g of x minus the derivative of x squared is 2x. We've seen that before.
G prime.
We're finishing right where the warm-up started.
Oh.
And then plus 0. And then we gonna go find f prime of 2. And I don't have g prime anywhere. So we're gonna come back up here. G prime of x, as Verge showed us on her summary of the yellow sheet, her little excerpt, I guess. G prime of x is e to the x. So that's going to be e squared. And that's actually the final answer because that does not simplify.
Hey, Mark, just move it down a little bit so that you're
oh, I'm probably out of my
just a little bit, yeah.
Just in case that was hiding behind my picture.
Yeah.
So right there.
And I love what you said there about the derivative of 3 g of x. You know, you can do product rule and get the same result. It's just going to take you longer.
Yeah.
And
the derivative of 3 is 0, right?
Right.
Yeah,
the issue is, especially as you prepare for the exam, is to be very fluent. And fluent means efficient and correct, you know, so
right.
So try and go to the direct, quick way of doing things.
Oh, did I lose somebody?
Nope, not me.
Okay, I heard a static jump that scared me.
So usually at this point in the lesson, we go back to our PowerPoint just to kind of wrap up a little bit and talk about what's in that shared folder. I left a lot of those circuit problems. If teachers want to give that as an assignment or work through those problems with their students virtually by conferencing, or if students want to work through them together with each other, great idea. Some of them are pretty algebra. Some of them are pretty algebra intensive on that circuit, but every answer should be found. Sometimes maybe working backwards. So now you know how to take a derivative, anti-differentiate. So you actually could maybe work backwards on some of them too.
That's true. Yeah, and you know, again, this is the link to the Dropbox. This QR code, if you take a smartphone and aim your camera at that, a prompt comes up to go to the link. That takes you to the top element of our Dropbox. In that Dropbox is this schedule. These 2 codes take you directly to that schedule. And again, you've got College Board has their resources up. And thanks again.
And tomorrow we're doing chain rule, and I can sing for that one too. Chain.
I knew where that one was going.
Chain of fools, right? That one. Who sang that song originally? Do you know, Mark?
I mean, I know there's an Aretha Franklin version, but
Yeah, is that her
Motown
song?
borrowed from so many others that who knows at this
Yeah.
point.
Aretha Franklin grew up in
Well,
Memphis, which is only
we're-
about an hour from me.
Well, I grew up 40 minutes from Detroit, and that's where the Motown sound was
Yes,
recorded.
big
so.
time, big time. All right, shout out to Detroit and Memphis today.
Thanks, everyone. We'll see you tomorrow.
Bye. See you tomorrow.
Little Richard.